Thanks. I'll begin with a word of prayer. Heavenly Father, we thank you for this day. We thank you for the break, which is about to start. Help us to glorify you what we do this day, Lord. In your name I pray. Amen. I want to start out with pointing out something that is, we can actually parameterize this curve if we use polar coordinates. Here's how. So this was r cosine theta, r sine theta, right? This is r squared equals to 1. So solving for r as a function of theta is actually not that bad. R to the 4th sine theta cosine theta, right? So therefore, r to the 4th equals to 1 over sine theta cosine theta. I could write that as 2 over, I'm tired of writing sine and cosine. I'm going to write that 2 over sine 2 theta just to be, right? I mean, you could put a 2 here and a 2 there. This is sine 2 theta, right? So therefore, at least for some points, r is equal to the 4th root of 2 divided by sine 2 theta. And that allows me to create the following natural parameterization. I can do x is equal to 2 over sine of 2t to the 1/4 cosine of t, and y is equal to 2 over sine 2t to the 1/4 power sine t. And there you go. That's a parameterization of that thing we've got stuck on the other day. So using polar coordinate gives us another tool that makes the impossible possible now. I mean, we tried our best in Cartesians, and we spent like 10 minutes on it. We got nowhere, right? Look at this. It's not hard at all. All I'm basically doing is once I have this, I decide I'm going to use t as theta. I'm going to make theta my t. My parameter I'm going to use is theta. So this is r cosine theta, right? And this is r sine theta. That's the idea. Yep.
What's the benefit of using sine 2 theta instead of just keeping it sine theta cosine theta?
Oh, just so I don't have to write sine and cosine. There's really not much benefit. Also, confusing the students, always a plus. But no, I mean, it's also part of my larger program of trying to instill in all of you a better sense of what's out there trigonometrically, right? Yeah. That's one of the big ones, that sine 2 theta is 2 sine theta cosine theta. That's a fairly famous one. Okay, so that brings us to area. Let's talk about area in polar coordinates. So first of all, I should remind you, how do we calculate the area of like a sector? What if I had this sort of piece of pie with, you had delta theta here like that, and suppose this had radius r. What would the area of this be?
2 pi r times delta, sorry, pi r squared times delta theta over 2 pi if radians are 360 degrees.
So you think of it as pi r squared times delta theta over 2 pi. I think that is a very, very good way to think about it. Because what that formula says is it's proportional to the angle subtended. And I know that if the whole angle is 2 pi, then we get the full circle, right? We get pi r squared. Now, of course, this simplifies, right? But that's how I remember it, actually. That's very good. So this is 1/2. Notice pi's cancel, right? R squared delta theta. So what if I was to calculate like this, right? Again, delta theta, but suppose I cut this out, all right? So I'm only trying to calculate the area of this piece in here. So this would be R1, let's say Rn, and this would be the outer radius, R out. What would the area of this be? Let me submit to you, we can take the area 1/2 R out squared, delta theta, right? And we can subtract from that, that overcounts, right? That includes the piece that we're not trying to find the area of. So we just need to remove this piece, right? Remove that piece, so we subtract Rn squared delta theta. So the area of this is, in fact, so it's kind of like a piece of pizza with a very symmetrical bite taken out of it, right? I mean, if you had very, like these would, if you had teeth like this, you're messed up, right? Like if your teeth, oh no, that'd be right. You could have teeth like that. I was thinking your teeth would be like this, but I'm imagining eating the pizza the wrong way. Actually, that'd be really tricky to do what I'm thinking of. Let me stop doing that. Okay, so as being it was disturbing me what I was thinking. Okay, so R out squared minus Rn squared delta theta. So that's the area of something like this, right? Okay, so then we take a little leap ahead here, and suppose that you've got some region that is stuck between two angles. Let's say theta 1 and theta 2, right? And you can imagine taking, and also we suppose that we've got some sort of inner radius and outer radius, right? And here this could be R in, let's say R, sorry, I'll get to it eventually. This is R is equal to R in, which of course is a function of theta, right? It's not, it can vary as you go. And then out here somewhere, I've got my outer radius function. R equals to R out, which is again a function of theta, right? And I'm trying to calculate the area between those curves. So like this area. What's this area is my question, right? So the idea basically is just to chop it up into, you know, like a bunch of sectors like this, right? And then also you can chop like this, right? And so if you focus in on, say, just one of these, say this one here, right? Let me blow that up. What's that look like? What is that? So we're looking, so let's suppose that this point here is at R and theta in polars, right? So this point over here would be at R plus a little bit of R and theta in polars, right? This point up here would be at R plus a little R, comma, theta plus a little theta, whatever it is, in polars. And this again would be at R, comma, theta plus the delta theta in polars. Now what I'm supposing is that we take delta theta equal to theta 2 minus theta 1 divided by n. So I'm suggesting we partition this into like a fan with n folds in it, so to speak, you know, like chop, 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 n of them. And, oh, I guess I don't need to chop the other way. I'm sorry, I'm thinking calculus 3 right now. I'm an idiot. I don't need to do that, do I? I don't need to do, I'm sorry guys, I'm making this too complicated. We can erase that picture. What can we look at instead? I'm making this way too hard, guys. I shouldn't look at this. I should look at, we're in Calculus 2. I'm sorry, guys. We should look at this, right? Right? We don't actually even need to do it. That's next semester. We'll get to there soon enough. I'm sorry. I just, sometimes my default is Calculus 3, and I have a hard time not thinking those thoughts. So, yeah, so we want to cut it up into this n sectors that have, you know. So that's not the picture I want. What picture I actually want to think about. Sorry about that. I actually want to think about this, which would be, you know, essentially this, right? And you notice that if this, as n goes to infinity, it doesn't really matter if you're on one side or the other side, right? If you're at theta or if you're at theta plus delta theta, it's essentially the same angle, right? So the radius, the inner and outer radius change very little along this arc. So it doesn't really matter which theta you use in the limit. The area for this, if you say, oh, I would say the little bit area, the delta A, which should be what? It should be 1/2 R out squared minus R in squared, right? And, well, delta theta. And then to calculate the whole area, we just sum those up, right? To be more specific, I take the sum, you know, I equals 1 to, well, I'm sorry, maybe be a little bit careful here for just a second. Take the limit as n goes to infinity of the sum, I equals 1 to n of 1/2 R out at theta sub I squared minus R in at theta sub I squared times, well, delta theta. And here I'm suggesting that theta sub I is equal to theta 1 plus I delta theta. I'm partitioning the angles, starting at theta 1 going to theta 2, right? As n goes to infinity, that gets finer and finer and gets to be better approximation to the actual area there. But on the flip side of things, we can go back to Calculus 1 and recognize this for what it is, which is what? What is this actually? This is the integral from theta 1 to theta 2 of 1/2 R out squared minus R in squared d theta. And so there you go. That's the formula we're going to use. Area bounded by R in less than R of theta less than or equal to R out. Right? Sorry. Good grief. R in of theta less than or equal to R less than or equal to R out, which is a function of theta, and theta 1 less than or equal to theta less than or equal to theta 2. There's the complete and rather clumsy description of the area we're bounding. It's stuck between two rays and inner and outer radius. Okay? Now, I will attempt to do some interesting examples for you. Example 4 from your text. And this will give us further further experience with graphing also. Okay, so r is equal to 2 minus 2 cosine theta. All right? And this is for 0 less than or equal to theta less than or equal to 2 pi. Let's find the area. Find area bounded by this curve. This curve has a name. It is called a cardioid. Right? Now, let's use now, to be safe, whenever you're doing this, you have to come to terms with, is there an inside and outside radius? What does it look like, right? Until you make a graph of the curve, it's really not safe to calculate the area, is it? This was also true in Calculus 1, where you're calculating areas between functions, right? If you don't know which one functions on top and which one's on the bottom, and if they cross somewhere in the middle and you try to calculate the area bounded between them, you'll just be wrong, right? You have to come to terms with what it looks like. Same is true for polar coordinates. So do we do that by graphing? What I do anyway is I graph this, right? So graph r as a function of theta. What does this look like? Let's see here. I try to think about extremes. That can be, if cosine of theta is 1, it's 0, right? If cosine of theta is minus 1, it's what? It's 4. So this graph is going between 0 and 4, right? So to make my picture most useful, I should probably draw the r-axis down here, right? Now, when I plug in theta equals to 0, let's do 0. Let's do pi over 2. Let's do pi. Let's do 3 pi over 2. Let's do 2 pi. Plug in 0, what do we got? Oh, we got 0, don't we? Right? What happens at pi over 2? We get 2. And then what happens at pi? We get 4, right? 3 pi over 2. 2. 2 pi. 0. So it looks like we're getting like that. I'm trying to draw it. All right, so now we can graph this thing. So what's going on here? We start out, the largest we get is radius 4 at pi, right? So maybe we're over to here at radius 4 at pi. Let me call that, I'm just, it's not in any particular order. That's point 1. I'm just labeling so you guys can tell what I'm doing. The second point I find interesting is the origin. That's interesting. At pi over 2, where is it? It's at 2, right? I might call that point 3. Obviously, I'm not doing these in order. I'm just in order of my interest, not in order of... You guys can order them differently if you don't like my stupid numbering. For the fourth point I'm looking at, it's down here. You're like, why are you doing it in that order? I don't know. If you could explain that to me, that'd be wonderful. Let's see here, and you can pick a few more points, like what happens if we look at pi over 4? It's like there, right? So pi over 4 is pretty, it's not very far out, is it? It's like here. And if we were to extend back or over to here, this is the corresponding point, and that's in the way of my label, but like down here, right? And so if you keep doing this, you can see that what you got is something like this. So So if you have a very good imagination, you can see it's a heart, I guess. So cardioid. Yes.
I was about to ask, is that what mathematicians give their girlfriends on Valentine's Day? Box of chocolates, just like that equation.
I don't know. I had an ex-student that, well, anyway, I'll shut up. Anyway, so what's the area? So clearly, this one is nice in the sense that it looks like the inner radius is what? So to figure out inner and outer radius, what you have to do for your region is draw lines from the origin, all right? And if your line from the origin is always in the region, in other words, if the origin is part of the shape, then Rn is 0. So this is very nice. Rn is 0 here, and this shows me that Rout is just equal to 2 minus 2 cosine theta, okay? And so all we got to do to calculate the area is integrate from 0 to 2 pi, 1/2 of 2 minus 2 cosine theta, quantity squared, d theta. I was like, why is this? Oh, this is not example 4, by the way. Example 4, he calculates the arc length of the cardioid, which you can also do, but it's not as much fun. I'm doing area. So you can look at example 4. Wrong. Example 4 is about the cardioid, but example 4 says calculate the arc length of the cardioid. I can't read. All right, so this is actually simpler because this is just giving us what? We can factor the 2 out. That gives us 2 times 1 minus cosine theta, quantity squared. See, because factor the 2 out, that gives me 2 squared when I factor it. And then 2 squared over 2 is just 2. You multiply it out however you guys like. We should all agree on the end product, okay? Which is 2 minus, parentheses here. 2 times 1 minus 2 cosine theta plus cosine squared theta. I will share with you some of my tricks. This integrates to 0 because it's cosine theta integrated over a full cycle. That first piece integrates to 2 times 2 pi, right? This is a cosine squared, and you're integrating it from 0 to 2 pi. If you were integrating cosine squared plus sine squared from 0 to 2 pi, what would you get?
2 pi.
2 pi. But cosine and sine are symmetric as they relate to each other over the whole interval of 2 pi, so the answer is pi. If you don't like that, you could do the integral in gory detail. Here it is. It will work out to pi, I promise you. This is theta over 2, evaluated from 0 to 2 pi, which is pi. Again, the cosine 2 theta integrates to 1/2 sine, well, 1/4 sine 2 theta, which when you plug in 0 and 2 pi, you get 0. So that cosine 2 theta term integrates away. But the rest of it gives you pi, which is what I wrote down from a sneaky way of thinking anyway. But that's still multiplied by the 2. I should be careful. So what do we get? We get 6 pi. There you go. Okay. Let's try one that's maybe a little bit sneakier. Trying to find one here. Number 17, we'll try that one out. We're supposed to find the area of the inner loop of 1 plus 2 cosine theta. Find area of inner loop. Okay, so yet again, in order to make sense of this, we need to start by graphing, right? And the way to graph that is, let's think about this. 1 plus 2 cosine theta, it's going between 1 minus 2, which is minus 1, right? And 1 plus 2, which is 3. So we're looking at a plot that's going between, minus 1 and 3, right? All right, let's get started here. Split in 0, what do we got? We got 3, don't we? What happens when we get to pi over 2? We get 1, right? Because pi over 2 makes cosine 0, so we're down to radius 1. What happens when we get to pi? Pi gives me minus 1, right? What happens when we get to 3 pi over 2? We're back to 1 again. What happens when we get to 2 pi? Back up to 3 again, right? So, I think you can see what's happening here. There's a plot of our polar curve. Now we can use that to create the graph, right? I mean, I suppose there are other methods, but this is my method. And I think it works pretty well when you try it. Let's see here. So, and I think we could extend this backwards as well, right? I mean, this will go back like that to where this would be what? Minus this, well, this is minus pi over 2. So it actually hits 0 radius a little bit past. If I think about this big loop here, I'm going from radius 3 at 0, right? And at a little bit past, see that, a little bit past pi over 2, a little bit, let's see here how to say this. A little bit beyond minus pi over 2, a little bit beyond pi over 2 is where we're circling back to 0 radius. So it seems to me this is, that's a bad picture. Something like that, crudely speaking. And then how about, I mean, this over here is more of the same, right? The thing that I haven't described yet, let me do in red, right? So like the piece we haven't done yet is this piece right here, if you look at it, right? So that's that would be over there, except what? Right? Which means that it's over here. And at pi, so like we would have this at 1, right? but we don't because it's actually over here, right? And so that's the little loop they're talking about. So it's asked us to find the area of the inner loop. Well, we found the inner loop, right?
So we simply integrate from pi over 2 to 3 pi over 2.
Hmm.
No, it's not that simple. It's not that simple.
Yeah, right.
Is that two different integrals that you put out together?
Well, if we look at it, from pi over 2 to 3 pi over 2, we do have an inner radius and an outer radius. The inner radius is the loop, and the outer radius is the, which we have Johnny Green.
Yeah, but we can't use the,
Yeah.
yeah, if you wanted to calculate the area between these two, that's a nasty question. In some sense, that's kind of nasty because you want to use the same function of theta for the inside and the outside radius. Awkward. The question, though, is where... this is misleading, right? This is...
Well, almost
that's...
almost 3 pi over 2.
This
That's what it is.
this is not even true. I mean, it's and that's not color coded, right? So how do you figure out where the what this angle is exactly? I mean, how do you find these points? Is my question.
Set that our equation equals 0, 0.
Right. So we want to set r equal to 1 plus 2 cosine theta equals to 0. And what solution, I mean, there's more than one solution here, but the one we're looking for, of course, is what? The one that's around here, right? So this gives us cosine theta equals to minus 1 over 2. And so what is that? At the moment, we may just be a victim of my poor graphing. But the algebra will fix that. That's the nice thing. How do you solve this? I mean, you can use your calculator if you like, inverse.
Is that 5 pi over 6?
That'd be 4 pi over 3.
Very possibly. I have to think about it for just a second here. This is cosine, right? And cosine is, I know that cosine is a half at pi over 3, right? And this is pi over 6. And so it should be symmetric on the other side of that, pi over 2 rather. And so it should be pi, yeah, it should be pi over 2 plus pi over 6 by my reckoning, which is 3 plus 1 pi over 6, right? So 4 pi over 6, 2 pi over 3, yeah. So yeah, this implies that theta is, now that you could get from your calculator too, right? When you take the inverse cosine of something in your calculator, what are the answers? The answers are between 0 and pi. So it will tell you the correct answer. I mean, this actually, the calculator will find that one for you. And then if you just use the symmetry with respect to pi, you can figure out the other one, right? Because this intersection point is as far as from pi as that one is from pi on the other side, right? So like pi minus 2 pi over 3, of course, gives me pi over 3. So that says that the other theta is 4 pi over 3 on the other side. So this, so what I'm telling you guys is that after a little bit of tinkering, I figured out that this right here is 2 pi over 3, and this one right here is in fact 4 pi over 3. So, now we integrate, hence, thus, we want to integrate from 2 pi over 3 to 4 pi over 3, 1/2 r squared, which is what? 1 plus 2 cosine theta, quantity squared, d theta. That should give me the area of the inner loop. All right? Can you guys do that integral? I mean, I can't use my symmetry trick on this one. I'm actually just going to have to straight integrate it, right? I mean, there is a symmetry here. We could take the integral, say, I think one thing that would be probably a nice simplification, save us a little bit of work, would be say, you know what, this is really the integral from say, pi to 4 pi over 3, right? We can just use this half and double it because of the symmetry of the graph, right? So if I change this to pi to 4 pi over 3, if I cut the integration region in half in the middle, I can get rid of this half, and then I just got, you know, that squared, which is, well, 1 plus 4 cosine theta plus 4 cosine squared theta d theta. Which is going to give me theta evaluated from pi to 4 pi over 3 minus, well, plus 4 sine theta evaluated from pi to 4 pi over 3 plus, now what's the integral of cosine squared? Right? So it's theta over 2 plus 1/4 sine 2 theta. But I've got I'm multiplying by 4, so I get 2 theta plus sine 2 theta. Again, evaluated from pi to 4 pi over 3. So you cannot help but get a good, healthy review of your trig integrals in this part of the course, right? It's ramping you up for the final. You should be happy about this. One less thing to review, right? That's, what is that? That's pi over 3, right? Because 4 pi over 3 minus pi is pi over 3. This is plus 4 times the sine of 4 pi over 3. And then over here, you've got plus 2 times pi over 3 from the 2 theta term. And then plus the sine, good grief, the sine of, looks like 8 pi over 3. The sine pi term is 0. So whatever that works out to. Oh, well, that's a pi. 2/3 plus 1/3 is 1. And I don't know about the other ones. I mean, I'm not... Fine. I could go get my calculator, but, you know, here's the blast from the past. This is pi plus pi over 3, right? Which is sine pi, cosine pi over 3, plus the cosine of pi, the sine of pi over 3. So that's actually minus 1 times root 3 over 2. So this is minus 2 root 3. And this one is the sine of 2 pi plus 2 pi over 3, right? Which is the sine of 2 pi over 3, which is the sine of pi over 3 plus pi over... You can use your calculator, folks, or you can put me out of my misery and tell me the answer. It's more fun to watch me suffer, isn't it? You monsters. Let's see here. Cosine. Why didn't I just say times 2? What's wrong with me? Anyway, that's root 3 over 2, 1/2 root 3 over 2, which is root 3 over 2, I guess. You are allowed a calculator on your exam, you know. I mean, I don't know why you're doing this to me, you monsters. Plus root 3 over 2. I guess that's the answer. Oh, do you guys have your book? This was number 17. Number 17 of section 10.5. I'm a little nervous. What, can you check the answer for me or no?
I think the book only gives you the answers to the odd.
It's number 17.
Oh, is it an example?
It's number 17 of section 10.5. Before class, I said I wasn't going to work out the integrals. I was just going to use Wolfram Alpha to do the integrals. I should have stuck by that, you know?
They have 2 pi minus 3 square root 3 quantity, that whole quantity over 2, which...
Over 2, huh?
The whole quantity over 2. Wait.
Oh. That's not my answer. Well.
Will we be allowed a graphing calculator on the next test?
Nope. That's the integral. 2 pi over 3. 4 pi over 3.
Oh, this might be an example of the kind of
One.
steep bounds that we were speaking of yesterday. Their lower bound is 2 pi over 3 and their upper bound is pi.
No, but it's symmetric. So that's not what we problem.
Are you saying there's a hint?
Sorry?
There's a hint in there?
Well,
I mean, what are you looking at? I'm not...
Their lower bound for the integral is 2 pi over 3 and their upper bound is pi. But you were discussing, perhaps in a different context yesterday, on how different bounds for these... That's not the case here, though, because we see the measurably symmetric.
Well, yeah. 1/2 of... Just a second here, guys. 1 plus... What I want to check real quick, what's more troubling... It's more troubling to me if the integral's wrong, that's fine. I mean, it's not great, but it just means that I most likely made a mistake in the... Yeah, so the integrand agrees with them.
Yes.
So let me just check real quick. So guys, I hope that don't be distracted by the trouble of the integration. I mean, the integration went sideways for us in the last example. But I hope you see the larger point is you just got to find your R in, your R out, and you find the appropriate range of theta and do your integral. You need to do some problems for yourself before it really sinks in, but that's pretty much what's on the next test, right? I mean, I think that's the end of chapter 10, give or take. Now there are examples I need to add. The next section is Kepler's laws in polar form, which I'll talk about if we have time, but there are examples I haven't done yet, right? Like the horizontal vertical tangent stuff, finding tangent lines to polar equations. But as far as I'm concerned, I have covered now, from my part, the things which I feel like I need to show you for the next test. So starting Monday after break, just open season for homework questions, all right? And if you guys don't have questions from homework, I will just start going to the homework and working them, whichever one I like. So let's just finish today by integrate, 0.5 times 1 plus cosine of x squared from x equal to 2 times pi divided by 3 to x equal to 4 times pi divided by 3. See what we get. So you gave me a decimal. For once in your life, you gave me a decimal. You worthless piece of... I wanted to compare to the exact answer you just told me. It's no help, right? If I change that to... oh, there we go. Huh. Am I missing a minus or something? Oh, 2 cosine theta. 2 cosine theta. There's a 2. That matters. That 2. Huh. What was the answer you said? It was...
That's equivalent. They just had the entire numerator over 2, so they had 2.
Okay.
To the square root of 3.
So that is equivalent to their answer, and it is not my... I mean, I got the pi, right? I had the pi right. Something went askew with these terms. It's probably in my madcap trigonometry over here somewhere. Anyway, have a good break. Don't sweat that stuff, and I'll see you after break.